Hello everybody, welcome to cyberplace.org, the academic level online course platform for cybersecurity studies, the only website that is specially designed for university students majoring in computer science and engineering, as well as for high school students specializing in cybersecurity studies. The website presents 4 different learning subjects: network communication, cybersecurity programming in Python, operating systems, as well as network and web attacks, all in 5 different learning tracks: textbooks, video presentations, audio, multiple choice questions, and code challenges. I invite you to subscribe to this website, choose your preferred subject and learning track, and enjoy. Good luck. Welcome back to cyberplace.org, and today we're continuing our video presentations with Wireshark. Wireshark is probably the leading sniffer application that allows us to witness whatever transmission is going through our local area network, understand it, and investigate it. We'll get familiar with Wireshark, understand what capture and display filters are, and what are the features that Wireshark presents in order for us to analyze and assess several case studies. Wireshark is a sniffer that is basically eavesdropping on our network interface card. In order to start using Wireshark, we need to specify what NIC we want to eavesdrop on. For example, if we have a wireline one or a wireless, the ability to use this NIC is to direct commands to it via the device driver. For example, in Windows, we have a pickup device drivers that we can, for example, use in order to block incoming transactions of a certain type. For example, an IP address or a specific protocol that we want to block. When we specify a promiscuous flag within our recording, we are able not only to understand what communication is directed to our computer, but to witness whatever flows through our local area network, as long as, for example, we are using a multiplexer named hub, which is a fail-open mechanism rather than a switch that takes into its responsibility to forward the packets only to the destination MAC. When we specify a capture option, we specify the name of the file to be recorded and the duration it would be broken by, for example, several minutes or several packets, and so on. We can also make use of some of the Wireshark conversion tactics. For example, do we want to maybe perform a name resolution on the MAC to identify the vendor that maybe manufactured it, etc., etc. There are 2 main filters that are used in Wireshark. The first one is a capture filter. The capture filter basically directs the NIC not to forward us several packets of a certain type. For example, we don't want any ARP protocol packets flowing through our network, or we don't want any communication that is targeted or arriving from a specific IP, etc., etc. The control of the capture filter is very powerful and potentially dangerous, because if we stop any incoming ARP records, we might not be able to convert the IP to a MAC, and thereby we would not be able to issue any packets whatsoever from our computer. Let's see an example. use the ARP-A CMD on Windows, we can witness whatever pairs of IP and MAC are known to our computer per each interface. For example, this one, or this one, or this one. If we are using the ARP-A again and again, we see that this information is basically expanding. Every minute and every time we see more pairs because our computer fetches more information from the local area network. This is performed by basically crafting ARP commands. When an ARP protocol is issued, it asks the neighboring computer, as we saw before, who is the MAC which is associated with a specific IP on our local area network, being a computer, a router, or another IP-based device. We see that this information is growing by the minute. This is because we did not stop any ARP protocol packets flowing through our computer. But what happens if we go to the capture filter and specify no ARP? If we delete the ARP table in our computer, we can see that the ARP table is not growing. It basically displays only the static entries that were defined by the administrator of the computer, by the default setting of our operating system. By doing that and stopping any arriving ARP, we don't see incoming ARP packets flowing through, and the table does not grow. That means that if we want to send a packet to a specific IP and we don't have the translation from the IP to the MAC, we are not able to craft a layer 2 packet information. And by that, we cannot send any transaction. This powerful capture filter is accordingly both powerful and dangerous. We can see other information in Wireshark using a display filter. The display filter basically directs the graphical user interface to filter only for our display a specific mechanism, for example, only a protocol or only an incoming and outgoing IP specification, etc. The display filter does not control the network interface card as does the capture filter. It would provide us with all the information and we are able to analyze it as we want, and we are using a display filter to momentarily display to us only a specific type, a protocol, an incoming, outgoing IP address, etc., etc. This would allow us to investigate it in a much more easy and maybe rich format. Let's see the CMD command ping, which is basically an ICMP message. We will get familiar with ICMP messages later on, that sends a short command to Google in order to see what is the quality of the route between us and Google. We can see that the ping command is basically composed of 4 transactions, each one calculating the distance in milliseconds for the packet to arrive from our computer to Google and back. And the ping command summarizes that in an average notation. We can see Wireshark picking up all this conversation and portraying it in a very nice manner over the OSI model. We can see each one of the requests going from our computer to Google and a reply coming back from Google to our computer in the exact same millisecond gap, mentioning the round trip it took from us to Google and back. And this repeats itself 4 times, the same as is reflected in the CMD command window. Each packet is displayed in an OSI level hierarchy with the physical data link, IP, and the IP payload, which is the ICMP command that specifies exactly what packet was sent, and if possible, the ability to also translate it to an ASCII file notation. To summarize, we have seen 2 filters, one which is a display filter and one which is a capture filter. The display filter is very easy to use, is very broad and rich, allows us to use advanced logic of equal and not equal and specific fields within each header of a protocol, while the capture filter is very limited and allows us only to block or unblock specific protocols or IP directives. The level of the application that runs the display filter is Wireshark, while the capture filter is ran on the device driver and the operating system, thereby blocking or unblocking beneath the application level on a root level. The activation that can be done on a display filter is very flexible. We can do it on the main sniffing window whenever we want. Before the recording, through the recording, we can change our mind. We can set with the initial display filter and change it through, while the capture filter directs a recording before it starts. It's done on the capture option screen and cannot be changed throughout this directive. Only when we stop the recording, we can change it again because this directive is physically sent to the device. The speed, of course, has its merits and downsides. The display filter is done by the program, by the application, and is therefore a bit slower, while the capture filter is done by the hardware on the NIC, and it's fast. We need to understand what is our objective. Do we want to block several packets? Do we want to get everything and later on filter it through our need? This is what would direct us to use a display or a capture filter. We can see the output of Wireshark in a very vivid style. Let's say by the OSI model, the physical layer 2, 3, and 4. We can see that layer 4 is using a UDP protocol carrying a level 7 protocol, which is called Domain Name System, DNS. We can see all its header fields on every level, understand what protocol is carrying which one on the next level, understand all the packet information in a hex byte notation, and if possible, also convert it to ASCII. For example, we can see that this is a DNS transaction to Google. Each, let's say, display filter presentation allows us to witness all the incoming and outgoing packets with their index, the time of arrival since the start of recording, the source and destination packets with respect to the MAC, if it's a layer 2 protocol, or an IP, if it's a layer 3 protocol and above, specifying which protocol is basically sent, and if possible, a short information that represents what we have seen in the presentation, in the packet. We can use various advanced features. For example, finding a packet which basically answers a certain filter. We can also color code it if we want to pay specific attention to an error or a problematic packet, let's say TTL exceeded ICMP message or a retransmitted TCP packet, and so on. We can use advanced features through our menu items. For example, understand the TCP stream that underlines the entire conversation with a get, a post, and answers of an HTTP protocol that's currently going on in our system. We can also use very clever display filters. For example, this one specifies give me all the packets which were either sent or received by a specific IP. This one directs only a destination IP, and this one specifies all packets which were sent from this IP. The same goes not only to the layer 3 header, but also to layer 4, specifying the incoming and outgoing ports. This one is a web, an HTTP listening port, which would allow us to maybe filter in all the web, let's say, transactions that were witnessed by our computer. We can also impose more clever and sophisticated logic, for example, using AND, thereby specifying we want to see all the transmission that is associated with a source IP of 217, etc., and a destination IP of 128, etc. We can specify also domain names. For example, please display for us all the communication which is associated with a certain school, which is called, let's say, Deshalit. And we can see all the information that flows through in an IP notation, because Wireshark knows how to translate a domain to an IP using the DNS mechanism as we see here. So the 104 is actually the Deshalit domain that we can see in this filter. We can basically use any filter with respect to logic transactions and to header fields. For example, header fields of the physical layer, starting with frame, or header fields of the second layer, starting with ETH, with the Ethernet, or IP, mentioning third level, let's say, notation, etc., etc. To finalize this part of the presentation, let's understand what is the difference between this notation and this one. This is a more clever and maybe tricky question, because an IP-ADDR is an OR logic between the source and the destination IP. When we're saying IP-ADDR not equal, we're basically not saying anything, because it could provide us with those packets that have an IP source of 10.0.0.1 while not an IP destination, thereby answering this request. This is the right approach, saying let's filter out all those which are either source or destination. So this notation is wrong. We can see the 10.100.102.6 here. We didn't block it in its display view, while this filter says, please do not show me anything associated with 10.100.102.6 as witnessed here. We'll continue our presentation with some case studies.